Okay, welcome everybody who's watching. I'm currently talking to you about second order conditions of constrained optimization problems. I have to say I made a mistake in the previous lecture. Well, sorry, I made a mistake when creating the slides that were used in the previous lecture. It was noted at the time that I actually thought it should be L instead of F here, and I've corrected it. So now it has an L instead of an F inside the bordered Hessian. And when you're taking these second order derivatives, you should be taking these second order derivatives with respect to the entire Lagrangian function, not just the objective function. So please remember that. Even though it won't matter for any time the constraint is linear, it won't matter, but still good to know. Now I was making this point that anytime you're doing a minimization problem like this, find the minimum for x and y of this function fxy such that something. Let's say you're so used to doing maximization problems that you don't want to do as a minimization. That's fine. It's exactly the same as this, isn't it? Maximize negative f of xy, right? To maximize the negative, sometimes it's called the opposite of a function, but -1 times the function is exactly the same as minimizing the function itself. So this is partially why I feel free to mostly just talk about maximization problems, because even if you do have a minimization problem, it's really equivalent. It's equivalent to just maximizing the thing. And if you think back to unconstrained maximizations, and we talked about concavity and convexity, you might think, well, wait a second, doesn't this change the concavity or the convexity? Yeah, it exactly flips it in exactly the right way, where if you had a second order condition that said before, how do we know that's truly a minimum? Well, f has to be convex, and then we know it's a minimum. Well, how do we know this is truly a maximum? Well, f has to be concave, then it's truly a maximum. Well, if f is convex, then negative f is concave. They have this nice property too. So even those second order conditions and everything else will still apply if you make this flip. And of course, it's totally up to you. It's like, what problem would you like to solve? The one on top or the one on bottom? Either one, you'll get the right answer. But just don't get confused, I would say, with these definitions. For those it does matter, you do have to remember, for a bordered Hessian constrained optimization problem, positive determinant implies the maximum, negative determinant implies the minimum. You guys are okay with this, right? You have any questions? I'm going to clear my drawings about this stuff. Good. I hope you're not too concerned about the quiz. I think you should be able to handle it. One thing I did do is included a parameter, and that's just to make the problem a little bit different than the ones I've already given you. And that is, you have to recognize what's a parameter and what's a choice variable. I'll write the choice variables right underneath the word max, or actually, I have to say this, when I'm using Blackboard to type in the formulas, sometimes the choice variables, at least in my computer, do not appear directly underneath the word max. They'll appear more like a subscript, which is down and to the right. I hope you guys are okay with that. Sometimes, it kind of looks like this: max, and then down here is like x, y. And sometimes I'll even do like this: greater than or equal to 0, or something like this. You should just pretend that those are when it's written like that, kind of as a subscript, that just means for whatever reason the typesetting isn't typesetting correctly, and it's I would prefer that to be directly underneath the word max, but maybe for some reason I just couldn't get it to do it. Please don't hold that against me, and still understand that these are the choice variables. Okay. Let's talk about, can we do another problem? Oh, we were in the middle of a problem last class, if you remember. We were talking about cost minimization. Here's another example. We're minimizing rather than maximizing. But I think we chose to leave it as a min, I believe. We didn't flip it to max. We left it as a min. That's fine. I'm going to go now back to that problem. Here's where we were. Let me remind you of the problem. We're talking about a firm who wants to produce 100 units of an output. And this is their production function. So they can, if they have K units of labor, capital L units of labor, then the total output is the square root of KL. In other words, they want the square root of KL to be 100. That's their output that they need. The thing they're trying to minimize is the cost, which was R times K plus W times L, which again is a very standard formula for costs in economics. In accounting, it's way different. You guys have ever taken an accounting class, they have different definitions for costs than we do. They have different types of costs. They have different, just different ways to measure the profits and costs, revenues of a business. In economics, we try to make it as simple as possible. And in doing so, we really just are talking about the opportunity costs of that capital and labor. We're talking about the rental cost of capital, not the actual cost of the materials used to make the goods that you're producing. Anyways, let's go on. In fact, we have already gone on. We made it past this slide, I think. Or did we make this slide? We didn't make this slide. We were somewhere between here and here, I think, last time.
I think we only found the first order condition of K.
Of K?
Yeah.
All right. So is this what we found for K? Something looks like this, where we have the derivative with respect to K of 5K becomes 5. For 8L, it disappears. Then you have this big term here, and you want to take the derivative of that whole thing with respect to K. K is the first, yeah, see, I've written here minimum K, comma L. So I think of K as being the first choice variable. That's why there's an FOC1 here. That's just my convention, which you're more than welcome to use.
And then
so we have
got,
go ahead.
Sorry. Oh, I think we got like 5 equals. Sorry, I'm just trying to remember.
Yeah, so what I did is I solved both of these first order conditions, and then I tried to simplify them and combine them. I remember I did that last class. And I got a relationship between K and L, but we weren't done yet. We didn't solve the problem yet. So now let's go back and do this sort of along with the slides. Okay, and the way I did it on Tuesday was not wrong. You can certainly get an answer that way, but because I don't have all of that written out, saved, let's look at what I have written here on the slides as a method. Just make sure you understand it. If you understand it, we'll move on. But like I said, let's take the derivative of this with respect to K. This final term here, lambda 100 minus the square root of KL, the lambda remains because this lambda will be multiplied by this term here, which has a K in it. That's where this lambda is. The negative remains. There's that negative. The 1/2 comes from that's the power of this KL term. It's being raised to the power 1/2. So that's where this 1/2 comes from. We have to reduce that power by 1. 1/2 minus 1 is negative 1/2. That's where we get this term. Everyone see how we get that? And similarly for FOC2. The difference is being it's 8 instead of 5, and there's a K here instead of an L. Oh, by the way, I don't know if I mentioned that, but that L comes from the chain rule of taking the derivative of what's inside here with respect to K, you get an L. And when you take the derivative of what's inside here with respect to L, you get a K. That's the only difference there and there. I think what's the best thing to do here maybe is to set yourself up to eliminate lambda. That's what I always do in a problem like this. Get rid of lambda. If you can do that, you're making progress toward finding a solution for sure. So let's try to do that. I'm going to solve the first order condition right now in terms of lambda. It's equal to 10 square root of k over square root of L. That's what these exponents are telling me. That's from the first order condition. From the second one, we get this 16k to the negative 1/2 times L to the negative 1/2. We can set these two things equal to each other and essentially move the L to one side and move the K to the other. And you will get this exact relationship that I got before using my screen annotation, but now you can see it on the slides. Do you want me to write it out, how we would combine this and this?
Well, how are the 5 and 8s getting doubled? I'm trying to.
Oh, sure. Yeah, so I'm moving this to this side. I got to annotate. Annotate always is good. Move this whole thing to the other side, then multiply by 2, and you get this. Then bring the L to the other side, bring the K to the other side, and you've isolated lambda. And do the same thing here to isolate lambda. Now you can set this equal to this, you know. What I have found for lambda, it's something now 16. Oh, that's a bad 6. K to the 1/2, negative 1/2, sorry. L to the 1/2. Hopefully you guys have, maybe this class has helped you get better at algebra, I hope, and more comfortable with using exponentiation and how to simplify exponents, because that's just something you do a lot in economics. Like if you see a K to the 1/2 over here and a K to the negative 1/2 over there, you should really quickly think to yourself, oh, if I bring that over, if I bring this K to the negative 1/2 over to this side, it will just be K. Won't that look much nicer than what I have? You understand why that is? See this K to the negative 1/2? If I essentially multiply both sides by K to the 1/2, this will go away and it'll appear here as K to the 1/2 times K to the 1/2, or just K. That'll be a really good way to simplify this. So I'm going to do that. Multiply both sides by K to the 1/2. And I'm also going to multiply both sides by L to the 1/2. That will make this term go away and it'll turn this term into an L. So here's what I'll be left with. 10K equals 16L. I got that just by simplifying this. It looks like a hot mess right here, but with some real basic simplification, it looks like this 10K equals 16L. I probably want to solve for K in terms of L and get what's 16 over 10. It's 8 over 5. I prefer that. 8 over 5L. You might say to yourself, hey, that's exactly the ratio of the input costs. Yeah, it is. Will that always be the case? Well, it depends on your production function, but yes, if your production function looks like this, then this will always be the case. It'll just be R over or W, or is it W over R? 8 was, which one was 8?
8 was W.
8 was W, so this is W over R. Yes. But we found that using the method of Lagrange multipliers. It just so happened that we eliminated the multiplier, lambda, and then simplified the equations and got down to this K equals 8 over 5L. We're still not done, you know, right? Don't answer a question in terms of the choice variables. That's just wrong. You want to answer it now. If it's answering in terms of a parameter, that's okay. You see the difference? Like if L were a parameter for some reason instead of a choice variable, then answering K equals 8 over 5L, that might be a perfectly good answer to this question. To solve this optimization problem. Well, you're solving it in terms of a parameter. That's fine. But if L is a choice variable, that's not a solution. That's just some condition that might be helpful in finding the solution, but it's not the solution. So how do we find the solution? We need to use the third first order condition, the one we haven't used yet. The one that's always just gives you back the constraint. So without even having to write it down, I just remember what the constraint was. It was 100 equals the square root of KL. I'm just writing the constraint again. Remember, the problem said, this is a firm that has to produce 100 units of output. And the way that it produces 100 units of output is by having K times L, the square root of that being equal to 100. So this is our constraint. Remember how I said, oh, constraints are always linear in the consumer choice problem. Well, this isn't a consumer choice problem. This is a cost minimization problem. And that's why the constraint is not linear. It's definitely not linear. It's got the square root function right here. Okay. Let's plug this in. Let's plug K equals 8L into there. What will we get? I mean, that's what we have to do to solve it. There's no other way to solve it. You've got to plug, once you've eliminated lambda and you get a condition like this, you got to plug that back into the constraint. What will you get? Instead of 100 times the square root of KL, K is actually 8/5, so it's 8/5 L squared. Is that right? It's kind of ugly. It's going to be a lot of irrational numbers here. The square root of L squared is L, but the square root of 8/5 doesn't simplify, unfortunately. Whoops. You're going to get an irrational number here, but that's okay. Let's try to solve it in terms of the irrational numbers. You can split this up to like square root of 8/5 L. So actually what we want is L equals 100 over the square root of 8/5. Another way to do that is 100 times the reciprocal of 8/5, which is 5/8. Sorry, this is not a great penmanship, mousemanship. But I think that's it. That is an answer for L, if I did all the math correctly.
I did. I solved it like a few minutes ago, but I just took like the square root of 100 and then multiplied it by 5 and then did like the square root of that to get rid of the L square. Would that be wrong?
Say that again. You took the square root of 100. That's 10. Okay.
I'm sorry. No, I squared 100.
Oh, okay.
And then.
Oh, so you got KL equals 100 squared. That's fine. That's correct.
Okay. Yeah. Yeah, I ended up getting L equals the square root of 50,000 over 8.
That might be,
thing?
yeah, that's the same thing I have.
Okay.
50,000. Yeah, if you put this 100 inside the square root, that's exactly what you would get. 5 with 4 zeros. 1, 2, 3, 4 over 8.
Okay.
The square root should go all the way down to there. Yeah, it's the same answer.
Oh yeah. Okay.
How about, do you know what actual number that is? You put that into a calculator.
79.1.
79. I have a school.
Yeah, point like.
That's just good. 79 is good. That sounds right. And how about for K?
K, I got 126.5.
126.5. You know what? That sounds right to me. What's happening here? I'm choosing to use more capital than labor in my input. Like, how do I minimize my costs? I'll be using more capital than labor. Why? Because capital is cheaper than labor. Capital is cheaper than labor, so I'm going to use 126 units of that and only 79 units of labor. You might say, well, why don't you only use capital? If capital is cheaper, just pump everything into capital, forget about labor. You can't do that. labor is an important part of your production function. If L goes down to like 0, then there's no way you'll ever get to 100, no matter how large K is. So yeah, this sounds like a very correct answer to me. But does everyone see how we got it? Anyone have any questions about this process? This is the process of Lagrange multipliers. We added this lambda variable in there just temporarily. It was just there in order to relate what's going on with the constraint to what's going on with the objective function. That's really the purpose of the Lagrange multiplier. But then once you eliminate it, once you solve for lambda and eliminate it, then it's gone. Then you're just talking about optimizing just the choice variables K now. If the problem asks, go ahead.
Oh, sorry. What was the point of the R and the W? Like, I'm just looking back at the actual original problem, and like, why do we have different letters? Why do we have to switch to K and L? How do we know what to switch to, I guess?
The question is, why did I call this R instead of just saying it was 5?
Or just saying it was K, since we ended up switching it to K anyway.
Oh, no, 5 is not the same as K.
Oh, really?
Yeah, no.
Oh, because we just solved for K. Okay, maybe that. Yeah.
Right. So be careful here. It's the cost of K. So the amount of money you spend on K is R times K.
Okay.
Yeah, it's not equal to K.
Okay.
And the reason I do this is because it's standard in theory of production. First, example 1 was the theory of consumption. This is the theory of production. Why do firms do what they do? The answer is they minimize costs given their output, and also they maximize profit given their cost minimizing way to produce it. So it's really all part of the same thing, but I chose to define R and W exactly this way, so it's consistent in case you see it in the future. Some theory about the firm and how it produces what it produces. Sure. What I didn't give you in the problem is just the formula for cost. And you know what? I don't think that's that important. It's just this. It's always RK plus WL. This is a generic formula for the cost of production. Of course, it's not always true. It depends on your model. But a very common model or theory of the firm is to sort of boil down all of the firm's costs to either capital or labor, and it's R times K plus W times L is what we think of as the cost. Even if you're, let's say, a pizza shop, you're making pizzas, and you have to buy dough and tomatoes and pepperonis and all these ingredients, you just ignore all of that. You ignore all of the materials, the cost of the materials that go into production. You might say, what the heck? Those are really important. Why would you ignore all of those? Well, there's a reason. Economists aren't just doing this. Some people blame economists and say, oh, you guys are always just assume away everything just to get what you want. Well, no, there's a reason. It's all about how things are defined. If the thing you're producing isn't just the final product of the pizza, but the value added of the pizza, right? You're actually producing something which is the difference between the value of the raw materials and the value of the finished product. Whatever that difference is, that's what you're producing. And that's why you can ignore the costs of the materials that go into the production. Right now, I'm just explaining to you, or rather justifying to you, why economists in their textbooks, right? If you picked up a textbook about microeconomic theory, and you looked at production, you looked at the theory of the firm and why does it produce what it produces, it completely ignores any sorts of costs of the materials, the raw materials used in the production. And why does it do that? Not because it doesn't feel like it. It's because there's certain other things that it's more interested in analyzing and proving theorems about. But it's not all just made up. Hopefully, maybe I've convinced you that, maybe I haven't. But given that, go ahead. Yeah, given that theory, it's always just RK plus WL. And and R happened to be 5, W happened to be 8. And that's where we got the Lagrangian, this subjective function here. The thing that we're trying to minimize is RK plus WL. Okay, how much time do we have? It's 1:09. Class ends at 1:45. What do you think I should do? Should I just give you the quiz now? Give you the rest of the class period to work on it? You guys have any other questions? Other than what's on the quiz, what are the answers to the quiz, and give me the answers to the quiz. And why are you not giving me the answers to the quiz? No, those are not the questions that I want you to ask. But I can answer other things if you have any. I think my third example, if I choose to give you a third example, it's going to take a bit longer, so I don't even want to start really. Oh, I didn't show you this, did I? Yeah, this is what you get when you plug it all in. Same thing. Here's the formula Kai got. The square root of 50,000 over 8, which is 79.1, and K is 126.5. It seems to be a constrained minimum. Should we even bother with the second order conditions here? What do you guys think?
You mean for the quiz?
So for the quiz, I do ask you about the second order conditions, but I told you that was for the case when your constraint was linear. In this example, the constraint is not linear. What does that tell you about H? It's going to be more complicated, H bar. The bordered Hessian is going to be a lot more complicated here.
It would have variables in it, right?
It would have variables in it. It could even have lambda in it. Right? Have you thought about that? If you took, where's the Lagrangian? Let's go back to the Lagrangian function. Here, this Lagrangian function has a lambda in it. Now, luckily, it disappears in a lot of cases. But in this case, it's not going to disappear. If you tried to take the bordered Hessian of this L, it would have a lambda in it. And what that means is to properly use the second order condition for this problem, you would actually have to find lambda star. I'm sloppy here. I didn't put the stars in. This should kind of be, you don't have to put the stars in, but the fact that you think this is a solution means call it L star, and this is like K star, the sort of potential solution to this problem. There's also a lambda star out there. And lambda star would have to be found like with this formula here. 16 times K to the negative 1/2 times L to the 1/2. You'd have to calculate it with these numbers, and you would get some number for lambda. And your bordered Hessian, it's often called H bar, H with the line on top of it. That's going to be this thing here, which is 0. That 0 is easy. But then just even the GX, GY are going to be complicated things where you have to evaluate it at this L, this K, and this lambda. Oh wait, no, the lambda will go away for that. But the lambda won't go away for the LXX term. You'd have to take the second derivative of L and with respect to X twice, and then plug it in what you found for L star, K star, and lambda star. What I'm saying is it's not going to be easy. I wouldn't even have time to do it. That's how long it would take. So I'm not going to ask you a question like that on a quiz. Maybe on an exam. Maybe if it was like a take-home exam. If it was a take-home exam, maybe I would have you go ahead and do all that calculus that's involved with finding these 4 second-order partial derivatives. But it would be time-consuming, and then also arithmetically consuming, in the sense that there's a lot of numbers being plugged in and calculators being churned out to finally arrive at this question: is H bar positive or negative? But I am sure in this case, H bar would be negative, which means this is indeed a minimum. How could I be so sure? Well, just look at the problem. Look at the problem. The problem is one of cost minimization. Could there be some other way to minimize cost with a different K and L? Well, no. The further away you get from the K and L we found, the more sort of extreme this you're gonna, like, let's say L gets really, really small. You're gonna need a ton of K in there, which is gonna drive up your cost enormously. Same thing for K. If K gets really small, then L has to be really big. That's gonna drive up your cost enormously. So just using intuition, I can say for sure, and you could say for sure that this is indeed a minimum. Now on a quiz, if I ask you to find the second order condition, then you have to give it to me. But just know that I won't ask you to do it unless it's something I think you can do that doesn't involve a ridiculous amount of calculations and lines of algebra, like algebra. If you're doing, more than one page of algebra for just one part of one question, I think maybe there's something wrong. I don't want to guarantee that, because of course it depends on how you write, what kind of a algebra dictator you are. When I'm talking about dictation, I mean, like, how many steps are you comfortable with going from one line to the next? Of course, the more you do it, the more comfortable you are with more steps. But if you want to go slowly, I don't want to stop you from doing that. You're totally allowed to, like, take your time and do algebra carefully. I'm not going to penalize you for that, for sure. So, okay, guys, I think I'm rambling. Right? You think we're ready for the quiz? If I make it available, I'll plan on giving you at least to the end of class, so at least a half hour to do this. Stop share. I have the quiz on assignments. It should be something that you see under assignments. But I have to edit the test options, if you don't mind. It is 1:16. I'll give you, how about 40 minutes? That's a long time. Hope that's enough. I do want you to complete it in one sitting. Oh, here's a due date. I really have a due date. I'll make the due date today. Hey, it's Earth Day, 4/22. Happy Earth Day, everybody. What time should I make the due time? Is it okay if I make it, how about 3 p.m.? I mean, I'll have another class there, so I won't be available to answer questions unless you ask them during class. But just in case for some reason you're having like internet problems, I'll make the due date 3 p.m. And sorry, every time I do this, I have to click what sort of formats and what sort of feedback you should be getting. Okay, it's available now. I think if you go to Blackboard under assignments, there should be quiz 5 available. And I will stick around for sure to answer any questions you might have. If you look at it,